On. All right, welcome, young astronomers. We're going to continue our discussions tonight about relativity and energy, kind of the rules of the universe, if you will. We learned, gravity is one of the dominant forces. We'll talk about the things that kind of oppose gravity tonight, but we still have to finish off relativity before we get there. Any questions or comments before I get started? I will answer the questions, the answers to the discussion, but I'll do that on a slide in a couple minutes here. Any other questions besides the discussion before we get going? All right, I don't see any, so let's finish up our slides here. Okay, so wait a second. Okay, hold on. Okay. Sorry about that. I just had it loaded up. I must have accidentally closed it. Here is where we left off. Remember, we were discussing the evidence for Einstein's theory of relativity. One of the ramifications is length contraction, given by that formula. A particle or a spaceship or you traveling close to the speed of light, you actually shrink a little bit. So you only shrink in the direction of the motion. Actually, this is, well, good we stayed on here. This is the answer to the first part of our discussion question. Probably the hardest ones for us to get our brains around. Because, right, the distance to some place is the distance, right? The distance to a star shouldn't depend on how fast you're traveling. Wrong. Maybe it shouldn't, but it does. Because you have to think about this in terms of relativity. Think of yourself on the Enterprise here, or the Discovery, or whatever I think the name of our ship was in our discussion. I think it was Discovery. We are, in our reference frame, we're at rest, correct? But if a person on Earth is looking at us going, 99.99, whatever it was, gamma equals 10, or 99.99% the speed of light, in our reference frame, we are stationary, and the planets, the planetary system that we're going to, which is a really cool planetary system, by the way, we'll learn about that in about a month, is coming towards us at that same 0.999 times the speed of light. Therefore, the distance to it, it's like that ruler, right, is moving towards us at near the speed of light. So that ruler is going to shrink. So the distance that we would measure on our spaceship will be contracted by that factor of 10. So it'll be 10 times less. Once we get up to light speed, or close to light speed, we look at our navigation system. It's going to look like that. I mean, not look like it. The TRAPPIST-1 will be 10 times closer to us than what we had measured on Earth. Like you could imagine, I don't know how we would build a spaceship to go that fast and not know about Einstein's theory of relativity, but just imagine all of a sudden in an instant, everything is 10 times closer than we thought it would be. I mean, maybe if we found an old spaceship or something and didn't know about relativity, you'd be in for a pretty big shock. I imagine the science officer on a ship that could go this fast would understand relativity. And so the distances are shorter. in the reference frame of them moving. And then we talked about time dilation. The time dilation is given by this factor. This means that again, one of the tricks here is the proper time. The proper time is the person who is at rest with the clock. So in our discussion, it's the twin who is traveling, who has a proper time. That means the time on Earth is going to be longer. So the people on Earth are going to think that trip took 10 times longer. And you see that 10 times is common between the two. People on Earth think that the trip took 10 times longer. The person on the ship saw that it would be the object is 10 times closer. If they both calculated the velocity that they went at, they both get the same answer. And so the law of physics is actually remains the same. It's the crazy, the time differences, the non-simultaneous that gets mixed up. So further proof of that crazy theory of the universe is actually, we have to find some crazy proofs, crazy things to prove Einstein's theory of relativity, right? We don't need it in the normal world. So all of my examples are crazy, right? They're all when we push the limits of our technology or the limits of at least our understanding in this case. We're going to learn in a couple of weeks that our atmosphere is very important to us, not just because we need to breathe that oxygen. Our atmosphere actually is a protective shield. It protects us from outer space. Outer space is cold, but it is very, very dangerous. We talked about how it warms us up, not enough, warms us up a little bit, not enough to, we still need the sun, but it protects us from what we call cosmic rays. Cosmic rays are highly energetic particles that some of them are produced in the sun, come towards us. Some of the cosmic rays come from the galaxy, even outside of our solar system. When a star explodes in a supernova, it produces a tremendous amount of particles. And Newton's laws, right? Those things could be traveling for billions of years. They're not losing any speed. They're coming at us from there. Actually, there's a hypothesis that one of the mass extinctions on Earth was actually caused by a supernova explosion in our galaxy. That kind of overwhelmed our atmosphere. It didn't destroy the atmosphere, but we'll talk about it. It depleted the ozone layer, and then the ultraviolet rays from the sun fried everything on the surface of the Earth. In that particular mass extinction, the sea life survived. It was just all the land animals that were killed, and not just the big ones like the mass extinctions. There's always something that survives. And when the comet killed the dinosaurs, it was the tiny little mammals. In this mass extinction, it was everything underneath the water because the water protects against ultraviolet rays, but the land animals did not have that, and we think it was because the cosmic ray flux was much stronger because of a supernova explosion, and it kind of it depleted the ozone layer. It didn't destroy the atmosphere, but for those of you who don't know, and we will learn in 2 or 3 weeks, the ozone layer protects us from the ultraviolet light from the sun. So this process, when there's not a supernova, it doesn't stop though. And normally our atmosphere is resilient enough to protect us from these particles. What they do is they hit the atmosphere, and these kind of looks like lightning, right? we're going to use Einstein's famous equation. Energy is equal to mass times the speed of light squared. Energy is equal to mass. And so this has a lot of what we call kinetic energy. If none of the, if this doesn't make a lot of sense to you, actually later on tonight, I'll define what I mean by kinetic energy. The energy of motion, right? You know when a car is moving faster, if you're in a car wreck and you're moving faster, it's more dramatic, it's more violent. There's an energy that's associated with motion. So these have, we call that kinetic moving energy. So these particles have a lot of kinetic energy, and when they hit our atmosphere, it's like a violent collision, but it doesn't just break apart these particles. All that energy can actually produce other kinds of particles, and we get what's called a shower. It looks like lightning, but it's actually a shower of other particles that are being produced. Actually, even particles that are more massive than a proton. Most of the stuff is protons or antiprotons or even electrons. They're pretty tiny compared to some weirder particles that they can actually make. I mean, this is nature's particle collider, right? The giant machines that we build to actually reproduce the conditions of the early universe. Is that me or one of you? But anyway, it's like a nature's particle collider. Hold on a second. I don't think that's me. Somebody whose computer is beeping needs to mute, please. Okay. Long story short, that was a long story. In that production of those cosmic rays, we make a cousin to the electron, which is called a muon. And a muon, we actually discovered these in cosmic rays, but we actually make these in the lab. They're actually interesting to study. This is like a cousin to the electron. Normal atoms don't have muons in them. This is like a heavy muon. It has almost all the same exact properties as an electron. It's spinning around. It has negative charge, but it's more massive, and it's actually unstable. It actually decays into an electron, plus some other stuff. But its average lifetime is incredibly short, 2.2 microseconds. So that means that even going at the speed of light, and these cosmic rays, many of them are going towards the speed of light. That means that even going that fast, they should not survive to hit the ground. We should only observe muons in the upper atmosphere. We do observe muons in the upper atmosphere, and we do observe more of them up there, but there is a significant amount of muons that actually hit the Earth. So that's just not possible. Muons without relativity. Without the time dilation effect, the muon would never live long enough, even at going the incredible speed it's going, to actually hit the ground. So this is experimental evidence for time dilation. The time of these, that proper time. This is the proper time. On Earth, we don't see the proper time. Our clock ticks. Its clock's ticking slower, but that's how it lives. So more time passes on Earth for it to die and so they can actually hit the Earth. You can kind of do a calculation here, and you can see kind of how it would how I get this 4 times 10 to the 8 meters. This is just our old friend D is equal to V times T here. So just the presence of them proves is evidence for relativity. Evidence that math is correct, not just a concept. We can actually measure the number of particles of these muons that actually hit the ground versus how fast they're going. Remember, they'll be more time dilated the faster they go, and therefore they'll live longer. And so we would expect more particles moving faster than the ones that are moving relatively slower. And we see that. So the fact that we see very few at 0.9, but 800 times more at 0.99c is actually more evidence for time dilation. It's actually evidence that our mathematical function is correct, that gamma t divided by gamma is correct. Okay, so here's kind of our discussion question. Not with crazy particles, but with people. We haven't done this yet. I mean, hopefully we'll get to see this. Hopefully, at least you'll get to see this. I think I'm not going to go over this. This is a different gamma, right? So at 99.99, we would have a gamma equal to 71. Remember, every little, and it doesn't seem like much, 99.99, let's go back to this, is a huge, right? Goes from 0.995, goes from gamma of 10, 0.99 is 22, 0.999 is 70. You add another one, you go to 233. Those are all the, tell you, how much longer, or the difference, let's say, between how the fast-moving person is going to experience time. So this is a little bit more drastic example. Let's say they were going to she's going to a planet 30 light years away at 99%. That's gamma of 71. She's going to so on Earth, right, 30 light years away, traveling this close to the speed of light, you could just do C. The people on Earth are going to think this takes 60 years, 30 years to get there, take a picture, and 30 years to come back. Our example was a little more complicated. You had to stay there for 10 years and study this system. I'll actually put the exact solutions to that on our help desk, just so you can check your math. But not to her, right? Her time gets dilated. Her clock moves slower by a factor of 71. So we just take however it took on Earth and divide by 71, 0.8 years. So she thinks she's gone a year. When she comes back, her twin brother is 60 years older. Okay, so this is the twin paradox. It's not really a paradox. It's just kind of weird. If you actually really study relativity, the first time you'll do this, you might think it's a paradox because, again, why is she special? Right, in her reference frame, her brother is moving away from her at the speed of light. So why doesn't his time get dilated? It has to do with the fact that she's accelerating. She had to get up to the speed of light, so she's the one who's moving, and she had to stop and turn around, and so she's the one that does that. Other examples of evidence for relativity have to do kind of like repeating the first evidence, right? The light being bent from the sun. In this case, it's not being bent from the sun. We actually have what's called gravitational lenses. We can look at a distant galaxy, and as the light from a distant galaxy passes through another galaxy, the light's going to get bent. In this case, it gets bent this way. It gets well, actually, we're over here. Sorry. So the light comes from my source here, some galaxy here, gets bent around. Sorry, goes back and gets around. Now we don't, as of yet, we don't have the galaxy mapped out quite good enough to actually see the difference like we did with the stars, where they should be versus where they are, or where they look like anyway. So what we rely on though, is something actually a little bit even more spectacular. If we take this piece of light and our eye stretches it back, it's going to see the galaxy over here. But also, the piece of light that goes on the other side of the galaxy, our eye is going to stretch it back here. So we actually get double images of galaxies. We get these crazy pictures. This is a picture from the Hubble Space Telescope that has a bunch of really bright objects called a quasar. We'll learn what a quasar is later on in this course. It's actually a supermassive black hole that's feeding and shooting out X-rays and light. These are some of the brightest objects in the universe. But there's no way that anybody could find 4 of these right so close together. That's just kind of crazy. But it's not. It could be possible. But then when we study these quasars, they are exactly the same. And no 2 objects in the universe are exactly the same. The tremendous, the trillions and trillions of planets and stars, some of them are very similar, but no 2 are exactly the same. These quasars are exactly the same. So we know that they are a gravitationally lensed image of the same quasar. And there's some gravitationally lensed galaxies there. They don't, the image is actually distorted. The galaxies, they don't look the same, but they have they're exactly the same properties. And then a handful of these things called Einstein rings, where the angle is just right, and there's we actually get a ring. This is just the image of one galaxy that's been kind of distorted and spread around a galaxy that's closer. A very massive galaxy. You have to have supermassive galaxies to get these Einstein rings. This one's not even, I don't think there's a complete one, but that's the closest one we have. Black holes themselves were predicted by Einstein's theory of relativity. Actually, Einstein, fun fact, did not believe in black holes. He said, we'll learn about this. Schwarzschild actually looked at his equations and said that there's a possibility of a dark star, of a black hole. And Einstein says, yes, the mathematics says that's possible, but Einstein was certain that some other law of physics would prevent black holes from actually happening. They don't, they're actually real. By the way, just because a theory says something is possible does not necessarily make it possible, mean that it's going to happen. Now, it is kind of an unwritten law of the universe that anything that's possible will happen. That the universe is either actually infinitely large or close to infinitely large, and it has a tremendous amount of objects in it. Just in what we call our little part of the universe has trillions and trillions of stars and planets. So yes, chances are, if there is something, if something is possible, then it will occur. But that's not true. Einstein's theory of relativity allows for you to go backwards in time, but there is another law of physics called quantum mechanics that it prevents you from going back in time. He thought the same thing would happen with black holes, but it does not happen with black holes. Black holes are real. For those of you out of the loop, we have a picture of one supermassive black hole. We have actual photographic evidence. This actually isn't the black hole itself. This is what's called the event horizon. The black hole is kind of inside of that, but we have this evidence of that. There's a supermassive black hole in the center of our galaxy, as we learned in our first week. We can actually kind of like the precession of Mercury was proof another proof of Einstein's theory of relativity. We look at the orbits of the stars closest to the black hole in the center of our galaxy. We've been doing this for about 25 years. And just like Mercury, the space-time is definitely not flat. These orbits are very strange. You need general relativity to understand the orbits that these stars make. So again, some more evidence for Einstein's theory of relativity. All right, those are all kind of weird, but there's one proof of relativity that we all, that we all use, and that is our GPS systems. Our GPS system has to be very precise, right? So, in the gravity well, or the curvature of space-time due to the Earth is not that big. I mean, it's certainly big enough to keep the satellites in orbit, and it's big enough to keep the moon in orbit, but all things being equal, it's not a very huge effect. However, when you have to be very, very, very precise, as in the GPS system, I don't know if you all know how GPS systems work, but it's based on, it's not really your phone sending a signal. Your phone sends a signal to Verizon or whatever, and then it bounces it off a satellite, not just one, a couple of these. And then it kind of triangulates, uses geometry by measuring how long it took that signal to get there. It can figure out where you are on the world. If you actually have a GPS device, then you don't need Verizon or whatever your phone company is. It will actually shoot the signal to the satellite itself. But you have to be incredible. It's measuring that time. And it turns out that there are 2 corrections that it has to make to that time in order to get the mathematics correct. One of them is the satellite is moving nowhere near the speed of light, but certainly, it's moving faster than the Earth. The Earth is moving pretty fast itself, right? 800 miles an hour, but this thing is whizzing around the Earth. It's got that 800 miles an hour plus the speed of the satellite itself. Don't get happy, I have a charger. This thing is moving faster than the Earth, and therefore, right, when an object's moving faster, its time ticks a little bit slower. So that's one correction. But also, if we look at the space-time well, or waterfall, or whirlpool, or whatever analogy you like best, the time gets dilated for the Earth. The Earth is deeper in the well. Space-time is relatively flat out here. It's more distorted down here. So by the gravity part of this, our time is ticking slower than on the satellite. They're not equal and opposite. We don't have an equation for this one. I mean, we do. Sorry, you don't. Our class doesn't. We can figure this one out. You know, it's incredibly small. You know, the gamma here is really close to 1, but you have to be really precise. So the engineers have to take that into account. There is Einstein's. There is an equation to actually calculate this, but like I said, that's a semester-long course. I got a semester-long graduate course to figure out the time dilation due to gravity. But you need to know the concept. Moving fast, the clock slows down, and they're moving faster than the Earth. But being in a gravity well, clock slows down, and we are closer to a person on Earth, or your cell phone is a lot more in this gravity well than the satellite is. So there's 2 corrections to the GPS. And it turns out that without those corrections, it would be off by 7 miles in an hour. Your GPS system. So there are real world consequences to relativity. And again, going back to this, doesn't mean Newton was wrong. It's a special case. It's a special case. It's actually a general case, right? The special case is really the other things, but in physics we would call this a special case. It's not always correct, but it's sometimes correct, and in terms of Newton, it's usually correct. But you think of Einstein's theory of relativity as a little bit of an add-on. And now there's a conceptual part here, Newton was wrong about the forces anyway, and actually he hated his. He did not believe. He actually wrote in his book about this, the fact that gravity acted over an infinite distance and was instantaneous. Einstein later phrased that as spooky action at a distance, right? How in the world, how in the universe does the sun know that the Earth has moved a little bit and changed its direction? Even Newton himself, he wrote in his book, somebody is going to figure out that this part of my theory is wrong. So he predicted that Einstein would come around and figure out what's really going on with gravity. Remember, gravity, it really is not a force. It is a curvature of space-time that does that. There may be somebody in this cartoon putting their hand on Einstein's shoulder someday. We thought, you know, that you can't understand the gravity just by understanding black holes and things like that. Actually, black holes is actually the example of this because, as we mentioned yesterday, the inside of a black hole, Einstein's equations don't work. They blow up into what's called a singularity, and people used to call the center of black holes a singularity or the Big Bang a singularity. But when a physicist finds a singularity, that means that there's a mistake someplace. Even the strange, weird, crazy worlds, there's no such thing as an actual physical singularity. There are mathematical singularities, but there's no such thing as a physical singularity. We can get things really, 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 really tiny, but not actually a singularity. A singularity would be an infinite amount of mass and an infinitesimally small amount of space. So that's one thing. There are, we're going to learn of dark energy. I mentioned them before, and dark matter. That have explanations, possible hypothetical explanations that we kind of add on to relativity. Maybe we don't. Maybe space-time we don't really understand at large distances, for instance. You know, that's the way science goes. We thought it was going to be Stephen Hawking putting his hand on the shoulder, but unfortunately he died. But many people are working on, we're still testing it. As I said, I wouldn't call it his theory of relativity if it had failed any of those tests. Nobody has explicitly said dark matter is a failure. You know, that's not, there's actually better, more likely explanations for both dark energy and dark matter than gravity being wrong. Okay, to transition into our last part of tonight's discussion is the famous equation. Energy and mass are intimately related. This is, as I mentioned, and as we'll learn, this is how the sun actually produces all of the energy by converting hydrogen into helium. And it turns out a helium nucleus is a little bit lighter than the 4 protons that are fused together to make it. It's a complicated transformation, but the start with 4 protons and you end up with a helium nucleus, and there's a little bit of mass difference between those that is converted, sorry Einstein, is converted into energy, or that energy transformed, let's say, into energy. I don't know the difference. That energy is manifested into heat and light. That's heat like that. So here, mass is energy. I said all that. There's a Big Bang, we'll learn. Particle accelerators, unfortunately nuclear weapons, all use this equation. What are the laws of the universe? We have Einstein's theory of relativity. I've mentioned quantum mechanics a lot. I'm probably we have to keep coming back to this. This is how the tiniest things in the universe interact, and they have ramifications to how the sun works, by the way. They're actually, we don't have to go to the sun. Why Jupiter does not collapse is because of quantum mechanics. So we're going to have to keep revisiting this. So we have quantum mechanics, we have Einstein's theory of relativity. We have what's called the standard model of particle physics, which incorporates quantum mechanics. And it talks about the fundamental properties of matter and forces. All of the forces of nature have actually a subatomic particle caused to them. The electromagnetic force, electricity and magnetism are actually a manifestation of a tiny particle called a photon that we've learned about, which is light. We'll talk about that next week in detail. But the strong and nuclear forces are propagated by tiny particles called gluons and W and Z bosons. And there are, this standard model is not just the atoms, it's beyond atoms. It's not just even the protons and the neutrons and the electrons in an atom. It turns out that protons and neutrons are made up of tinier particles called quarks. And as you saw, there's even other strange stuff there, like the muon. There's cousins to the particles that make up the building blocks of the Earth that are only really manifested in, we make them in the laboratory, but in outer space they can be produced in high energy interactions in outer space. And certainly at the beginning of the universe, that was what was produced, actually. So there's a couple of dozen of what we call fundamental particles. And protons and neutrons aren't fundamental. When I say fundamental, that means they're not made up of tinier objects. In the standard model, the proton is made up of quarks. The electron is not made up of anything. It's a fundamental particle. One of the outstanding issues, as I mentioned, is how does gravity fit into this? Is there a particle associated with gravity? Is there a graviton? If there is, we haven't found it yet, so we don't know how it fits into there. And underneath all of this is, again, we think that electrons are fundamental and quarks are fundamental, but that's a limit on our technology. So think's not the right word. We can't measure that they're made out of smaller things, but Rutherford couldn't measure that the nucleus was made up of smaller things. And as our technology improves, we can break apart. We're not splitting the atoms anymore. We're splitting protons. And we find that the proton is made up of something smaller. We have not yet split a quark or split an electron. It doesn't mean we won't. We may need another 50 years of technology to get the collisions violent enough to break apart a quark. There is a theory. It's an elegant and beautiful theory. And I mean theory with quotation marks this time. It's not a scientific theory, even though it has it in its name. It's called string theory. String theory. So even physicists, they make mistakes too. String theory is not a scientific theory because there is no evidence for it whatsoever. There's actually there's very few even hypotheses on how to try to prove string theory, other than breaking a quark apart. But it may well be. I actually think there is. This is one of my religions. People think that all scientists are atheists. Well, those that are atheists, this is their religion, is string theory. In fact, there's been more than a dozen popular books on string theorists who believe that they can disprove the existence of God because of their weird string theory. But so right now, string theory is a religion. It's one that I prescribe to, but I can't prove it to you. It's elegant, it's beautiful, it solves lots of problems in this standard model. The standard model is not perfect, but there's no evidence for it yet. All of the stuff in black here, there's lots of evidence for the standard model. It's not, none of these things, again, I'm not going to tell you they're absolutely true, because I can't. That's one of the premises of the scientific method. You can disprove anything. You can never prove that something is absolutely true. You would have to think of all the possible tests and then go out and do all the possible tests. That's not possible. And then you'd have to think about all the new technology that would give you more possible tests. It's not possible. But this is our best understanding of the laws of the universe. Standard model, quantum mechanics, Einstein's theory of relativity, and the law of thermodynamics, which is kind of how heat and information are transformed. And we'll learn about laws of thermodynamics as we need them. And we'll have to delve into more of the standard model and quantum mechanics also as we need them. One of the manifestations of those laws of the universe come in the form of what we call conservation laws. And the universe is ruled by several of them. Conservation of energy. Energy cannot be created or destroyed, but it can change form, right? I can convert protons into helium nuclei and energy and light and heat. Conservation of momentum. Is hard. Conservation of momentum is best is observed in car crashes, but you don't notice it. And we don't use conservation of momentum too much in astronomy. What we use instead is conservation of angular momentum, and that's actually easier for you to experience, as we'll see. Conservation of electric charge. Fun, embarrassing fact. You all, I assume at some point in your scientific learning have heard about electric charge, right? The charge of an electron is negative, the charge of a proton. We don't really understand what charge is. It's a fundamental property of matter that we do not understand. One of the things that string theory tries to do is explain what charge is, and it doesn't even do it that well. But it is a measurable quantity. We have learned that it is conserved in all interactions. Charge is conserved. I don't mean that you have to, maybe you could have several objects that are charged on one side of an interaction and several different. They can change forms on the other side using E equals mc squared. But whatever my initial charge of my system will be, the final charge of my system will be the same. And then this is one of the laws of thermodynamics, actually, is it's not really a conservation law, is it? But whatever. It's actually an anti-conservation law. Is that the disorder of the universe can only increase, and it usually does. Sometimes it stays the same, but it usually increases. Right? You have a wine glass which is highly ordered, and the atoms are all in a lattice, and they have this beautiful shape. And you drop it on the ground, and it breaks into many pieces. And that's you never see the opposite happen, right? You never see a bunch of glass spontaneously turn into a wine glass. Now you say, well, I made the wine glass, but yes, but you had to disrupt lots of other things to make that wine glass. You had to heat up an oven, and you had to take a bunch of sand and melt that into glass, and then you by making that beautiful wine glass, you actually, maybe if you're lucky, you kept the order of the universe the same, but more likely you produced more disorder in other parts of the universe to make that wine glass. This has to do with kind of the arrow of time. This is another reason why probably can't time travel. Quantum mechanics is another reason, at least backwards in time. Special note, matter is not conserved. I can turn protons into helium nuclei, and not even what we would, the mass of an object is not conserved. The mass energy of an object is conserved, but the matter part of that we would normally call its mass is not conserved. Okay. What is angular momentum? First of all, let me tell you what it is before we talk about this this equation. Angular momentum is the tendency of an object that is spinning to stay spinning. Okay, and you may say, well, that's not true. When I do a top, it spins for a while, but then it slows down. But try and do that top on some ice. The reason why a top stops spinning is because of friction. In the absence of any twisting force on an object, it will continue to spin. It's kind of like Newton's second law, only with rotating things. It's actually very much related to that. In fact, Newton's law is a special case. Newton's second law is a special case of conservation of angular momentum. Even though you're not used to that, this is what allows you to stay on your bicycle while it's rotating, right? When you're on your bike and you stop, those tires start to spin. They'll either stop to spin because of friction or you hit the brake. But when you do that, it's a lot harder to balance, right? But once those things are moving, you can balance easily because they're keeping you from falling over. We use this to turn and to keep turn satellites, but also to keep, like the Hubble Space Telescope, right? It took that picture at deep view. It had to keep tracking the deep part of the universe for weeks at a time, and so it uses what's called a gyroscope, a spinning a device that spins around to keep things on track. The mathematics of this is the angular momentum is equal to the mass times the velocity times the radius where most of that mass is concentrated. Okay, right, even though so let's talk about the Earth and the Sun. The Earth certainly has a force on it, right? But it's always what's called radially. It's not a twisting force. The sun's not trying to trying to twist the Earth around. It's just trying to pull it towards it. And so conservation of angular momentum, the Earth is just going to spin around, not spin, but orbit around forever and ever. And again, if there is a force due to the moon, but right, we talked about the Earth slowing down a little bit. If we didn't have the moon, the Earth would just continue to spin at the same rate forever and ever and ever. A demonstration of the radius part of that, which is an important concept that we'll use, is the figure skater. When their arms are out like this and they start their spin, they move slower. If they want to speed up, they take the mass and move the mass closer to them. Most of the mass is the same, but you have some mass out here when you started, and now you don't have any mass out there. So the mass is closer in, and therefore they speed up. And if they want to slow down, they just move their hands back out, and the opposite will happen. The mass isn't changing of the figure skater, but the radius in that equation is changing. The angular momentum stays the same, and therefore something's got to give. What has to give is the velocity, right? We have three things: mass times velocity times radius. The radius changes, the mass changes, and so our velocity has got to change. That all that together stays the same. You can actually explain Kepler's law with this. Remember that the closer an object is to the sun, the faster it's going to orbit. Again here, the mass of say this is the Earth. This is, by the way, this is a highly exaggerated ellipse. The Earth is almost perfectly circular, but not quite. But This is just an exaggeration. But when we are closer to the sun, we are moving faster than we are further away from the sun. That's, again, the angular momentum doesn't change in the orbit. So when one of those changes, the mass doesn't change either. So when it's the radius that changes, and and therefore the velocity has to change to counteract that. There are other kinds of energy. As I said, kinetic energy, the energy of motion. There is radiation from the light. There's radiation from the light that's not heat, right? For a lot of ways we actually equate those two, but light has energy beyond that, right? Your solar panels, they don't get hot at all, and so there's radiation of energy. There's also potential energy or stored energy, right? You actually one of the units of energy is a calorie. It's not the one that we're going to use in this class. We're not. If we use it, it'll be joules. I don't think we actually use it. It's in one of our equations, but it usually cancels out. But that's stored. That's chemical energy. Gasoline is potential energy, right? It's got anything that you can consume or that will produce energy has what's called potential energy. In fact, we consider gravity potential energy. The curvature of space-time is a potential energy, right? I can drop this pen and it will actually. It's got a lot of potential energy up here. It's actually it has no kinetic energy, right? It's got no motion relative to me anyway. It's got a bunch of potential energy because I'm holding it up in space-time, but if I let it go, I'm actually converting some of that space-time energy into that potential energy due to gravity, if you will, or due to space-time, into kinetic energy, right? You couldn't quite notice it, but it actually speeds up as it's going. As it's sucking in more and more potential energy, it speeds up. So again, conservation of energy. It can change type, but it cannot be destroyed. Another type of energy is thermal energy, and this has to do with it's actually kinetic energy, but you wouldn't imagine it, right? But you have to think about when you touch a rock that's been sitting out in the sun and you touch it, or worse, a piece of your car, right? Your car, the hood of your car, if it's really hot out there, you can burn your hands on there, right? You'll definitely feel it's a lot warmer. You might say, well, how is that kinetic energy? It's the kinetic energy of the particles inside of the hood of the car are moving around. They're bouncing around. That's actually what you feel as heat. You're actually feeling those particles, at least their energy fields, hitting your energy fields. And so thermal energy is kind of the average kinetic energy of the particles. And that's what we talk about this being, it's related to temperature, but it's not exactly the same. The thermal energy is the kinetic energy, but how is that different from the temperature? Temperature is actually the average kinetic energy of the many particles in there, but we can have different densities. We can have different number of particles in there. So, for instance, we can have an oven, right? An oven has a temperature of, let's say you have it all the way up 450 degrees Fahrenheit, right? As long as you don't touch any of the metal, you can put your hand in there for a while. I mean, you don't want to put your hand there for a long time. You'll cook your hand. But you can put your whole hand in there and it may seem a little warm. But imagine if you did, you had a pot of boiling water, which is only, what does water boil at Fahrenheit? It's 100 degrees Celsius, so don't laugh at me for not knowing the boiling point of water. I'm laughing at you because you use Fahrenheit. I think it's 212. Anyway, it's a lot. The temperature is a lot less, about half less than what's in your oven, right? You do not want to put your hand in there. You want to put a hand in there is because you have a lot more stuff in there, and actually the molecules are actually a little bit bigger too. So that's going to do a lot more damage. So thermal energy depends on the mass of what's in there, how much of it's in there. The temperature is really just telling you how fast they're moving. Oh, there we go. I got it right. I'd like to say I did that on purpose, but I really couldn't remember what it was. These are the temperature scales that we're going to have to use them. You might be familiar with these two, Fahrenheit and Celsius. But what we're really going to use is what's called the Kelvin temperature scale, because we need 0 degrees temperature to correspond to no motion of particles. And certainly this is not going to work. You know that, yeah, it's cold out there, but you can still breathe when it's 32 degrees. You don't have to suck in air. The air, as soon as you open the mouth, the air is moving. It will move into your mouth. And we can't even use this. Even 0 degrees Fahrenheit is not that cold. So we have to come up with another temperature scale called Kelvin. And this is the point of scientifically, we're always going to use either Celsius and Kelvin, and so there's a simple relationship between the two. You just add whatever it is in Celsius, you just add to 273.15. If you insist on using Fahrenheit, you will have to find the conversion factor, 5/9 F plus C or whatever it is. Don't quote me on that. And convert your Fahrenheit into Celsius and then into Kelvin. You know, I'll still try to, you know, if I'm trying to tell you how hot something is, like I did with the ovens, I'll still give it to you in Fahrenheit. But when we do calculations later on in this course, make sure that you're either in Celsius or in Kelvin. And you'll know which one to use because the formula will tell you which those are. Okay. I think we did all of this stuff. Okay. We can think of those orbits again. Let's revisit this. We can think of not just conservation of angular momentum, but we can also we can actually verify Kepler's laws with conservation of energy. Again, we want to talk about the energy of a particle, a planet or a satellite in orbit is equal to its gravitational potential energy and its kinetic energy. It turns out the closer you are to the object that's pulling you, right, the less potential energy is. And so we have less potential energy here. It actually goes as 1 over r, not 1 over r squared like the force does. It goes as 1 over r. We're closer here. That means we're speeding up there. And energy is conserved. The energy of this planet is conserved as it moves around. Even though it's getting faster, its kinetic energy is getting faster. The potential energy is smaller. We can actually think of what energy it would take us to actually leave to get where there was 0 potential energy from the due to the Earth. And then we could calculate using conservation of energy the what's called the escape velocity. Turns out that's about 11 kilometers per second. The concept I just want you to know is that you have to, you have to have enough kinetic energy to overcome the potential energy of the Earth. So orbits stay the same unless they encounter something else. There's a famous example of this in our book that Halley's Comet, or Halley's Comet if you're British, and he was, so that's his real name, but we call him Halley's Comet anyway. It changed. it still takes it 80 years to revisit us, but it used to take a lot longer. But on one of its trips, is orbiting the sun just like we are. But on one of its trips, it encountered Jupiter, and gravitational interaction between Jupiter completely changed its orbit. So it used to be what was called a long period comet. It was going to go like this. It would take thousands of years, if not hundreds of thousands of years, to make an orbit. But as it was going here, it got sucked into Jupiter's gravity well. It wasn't enough to crash into it. There have been comets that crashed into Jupiter. Jupiter kind of protects us from comets. Not always, as the dinosaurs will tell you. But sometimes it didn't hit Jupiter, but it completely changed its orbit. We actually use that for our spacecraft to conserve our chemical energy that powers the spacecraft. We use what's called gravitational assists to speed up our satellites and to change their directions, right? Remember, it takes a force even to get it to move. Even if you're not speeding up, it takes a force to make a satellite move, a space probe move. And so it takes a lot of energy, as you might have, to get something off the Earth. The more massive it is, the more energy it takes to actually get it going to that escape speed. And so we can't take a lot of fuel with us. So we actually use, it's like a gravity highway system of the solar system that we use. This was actually the path of not a very recent, but a spacecraft that actually went to visit Saturn. It didn't just fly straight to Saturn. It would take them too much fuel. It actually did. It was launched from Earth. It did an orbit of Earth. It did an orbit of Venus. Did another orbit of Earth, and did another orbit of Venus before it got going fast enough that it could go out to Saturn. So we actually use this gravitational assist to power our spacecraft. Okay, that's all for this chapter. Again, we've got some quizzes here. I think the quizzes are mostly the same as last week, actually. There you have it. That's all for tonight. As I said, I'll post the exact solutions to the discussion question on our help desk, since I don't think anybody's even looked at that yet. So you'll find out how to get there, and then if you got some questions, you can ask them. I mean, yeah, you have used them. That's not true, but not about more practical things. But yeah, okay. That is it for this week. Let me give you a heads up. Well, first of all, let's just right. You've same old. You got a quiz on this and a homework on this. Both of those are due on Sunday. The discussion is going to be a little bit different this week. I'm going to give you a little extra time. Before class on Monday, though, I want you all to have decided on a telescope that you want to write a brief summary of. All right. And it's going to be first come, first serve, like our evidence for thing. So when I say by Monday, I want you to have chosen a telescope that nobody else has chosen. So it may take you a while. I'll open that discussion up right after dinner. So you can, if you have a telescope that you love and you want to write a little brief thing about it, I can do that. And then, so by Monday, you'll have to have it picked. By Wednesday, before class, you'll have to have your write-up on it. And then I'll give you all until Friday to kind of talk to each other about what you found was cool or about each other's, it's like a blog or whatever, summaries. Okay. Any questions or comments on that? I do not see any. All right, everybody. Thanks for coming. And have a wonderful rest of the week and weekend. And I will see you all on Monday. Bye. Yep. Thanks, everybody.